Okay, this is Kent. It's Friday, and I'm re-recording Tuesday's lecture on negative edge lengths and all pairs shortest paths uh, because I forgot to enable the microphone on my screen recording on Tuesday. Similar to the first lecture. The same disclaimer that everything is set up to try to be kind of maximally interactive. So my expectation is that uh, uh, going through the slides without that interaction is probably going to take less than the usual hour and 15 minutes. And I'll try to remind myself to kind of say the questions out loud anyway, and so that you might want to pause the screen or something and somewhat simulate what it's like. Okay, so negative edge lengths and all pairs shortest paths. Um, uh, So let me just flash this as I have been for the last few lectures because I think it's counterintuitive. This idea that many problems are solved um, by two different high-level approaches. One is to try to identify the appropriate subproblems. At some level, try to identify the right induction hypothesis to break down your problem efficiently. That'll be a theme today as well. And another one that I think is uh, counterintuitive is rather than kind of changing and aggressively making a new algorithm from scratch, see if there's some way to change the input uh, and use an existing algorithm for which we've already analyzed and developed some very robust properties that you can use. And one thing great about both of these approaches is that it also greatly eases the burden of proof, um, uh, because usually at a high level things are kind of cleaner. It's more clear to see what's going on compared to kind of building algorithms from scratch from bottom up, which ultimately require a lot of care to do things perfectly. Okay, so we've been talking about directed graphs for a few lectures now. We will talk about directed graphs today as well. We started with connectivity problems in directed graphs. So can point A reach point B? We looked at DAGs, which is sort of the simple case, and they permit topological sorts of the vertices. And then we talked about, in general graphs, how you can use depth-first search to figure out all the vertices that S could reach. My impression is that many of you have seen depth-first search before this class. Then we started talking about strongly connected components and this idea that, if I'm interested in reachability and who can reach who, let me treat sort of as identical the vertices that are strongly connected with each other because they'll have the same sort of reachability relations as everybody else. So we have these strongly connected components where everyone within a strongly connected component is strongly connected. And what's really nice is that if I contract each of the strongly connected components into a vertex, the remaining graph is sort of automatically a DAG of strongly connected components. In a sense, this is sort of giving you a very compact summary of all the reachable relations. Okay, but that brings up this algorithmic question of how to get the strongly connected components. And it turns out that one can actually kind of use DFS and take advantage of the post-DFS ordering somewhat subtly, and get all strongly connected components in linear time. So then the next lecture on directed graphs was discussing this longest path problem. So here I give you a directed graph, maybe with edge weights, maybe unweighted, and I say what's the length of the longest path in the graph. Amazingly, we actually found a path with 10 edges, which I didn't expect. But in general, the problem is NP hard in general graphs by this kind of very creative ladder-like reduction. I can take a SAT formula and kind of turn it into a Hamiltonian path problem, where the problem the graph has a Hamiltonian path if and only if the SAT formula was satisfiable. This was in contrast to the problem in DAGs. So again, we have no cycles, and in particular, sort of the longest path problem is the same as the longest walk problem because if there's no cycles, there's no way to repeat vertices anyway. And walks are somehow much nicer because I don't have to keep track of which vertices I've visited and I haven't. So by now, we're getting a little more used to this idea that if it's in a DAG, there's a good chance that recursion might work really well because there's not as much cyclic dependencies. So we wrote, we set up the recursion for the longest walk algorithm. We applied dynamic programming, and in fact, you can find the longest path / walk in a DAG in linear time. And then we had enough time that class to also talk about sort of a problem that seemed to sort of be in between the two cases. So this problem was trying to find the shortest walk was a constraint on the number of edges. So I give you a graph with edge lengths, positive or negative, and the question is, can you get from S to T, or what's the way to get from point A to point B with at most k edges and a minimum total length? Okay, and at some level we're going to look at this problem today, but remove this less than equal to k. It wasn't clear at first, but we eventually stumbled upon this idea of, the point of this problem is that we have introduced cycles back into the input, but nonetheless we were able to do something recursively by introducing another parameter I, keeping track of how many edges I've used kind of so far on my walk. Or another way we look at this is sort of to build out a layered graph. And then last time we looked at shortest walks, shortest path problems, trying to compute distances, and we started with the case where the edge weights in a graph are positive. Today we'll remove that assumption. But the distance was defined as sort of the infimum over the lengths of all walks. So the distance for ST is the infimum of the length of all ST walks, which by definition means it's positive infinity if you can't get from point A to point B, and it's negative infinity if that length is arbitrarily small. It can be made arbitrarily small. Now for positive weights, we don't have to worry about negative infinity, and so we looked at kind of three kind of increasingly complicated cases. We started with a DAG, just trying to get the shortest walk from point A to point B in a DAG. And there being a DAG, we tried setting up a recursion and applying dynamic programming. This was actually very similar to the longest walk algorithm from the previous class. Next, we removed the assumption of a DAG, but for simplicity, we left the graph unweighted. And so kind of the theme of that discussion was, in the presence of when it's no longer a DAG, there's not a topological order to go by and stuff. So the induction hypothesis to make things work is not obvious. But ultimately, because the distances are all integers, we can do an induction on the distance. So S is the only vertex at distance 0, followed by the vertices of distance 1, distance 2, distance 3. The point being that once I know all the vertices at distance 1, it becomes much easier to identify the vertices at distance 2. Once I identify all the vertices at distance 2, it becomes much easier to identify all the vertices at distance 3, and so forth. Okay, and then from there we started talking about the weighted case. Okay, and there too it wasn't totally obvious how to make an induction argument out of it, especially kind of when the weights can be arbitrary and real valued and stuff like that, so they don't just naturally count off 1, 2, 3, 4, 5. But ultimately, we present Dijkstra's algorithm that runs in nearly linear time. And at that some level, that's sort of doing the ordering now is based on identifying the vertices in increasing order of distance. So the source S is always the only vertex weight 0 because I'm assuming positive weights. And now knowing the closest vertex, I can start looking at what's the next closest vertex. Okay, I should look at the edges leaving S. Now I know S and the first closest vertex. I can try to figure out the second closest vertex by looking at edges leaving S and the edges leaving that first vertex and so forth. But we can kind of count off who's the closest, second closest, third closest, fourth closest, and in general, knowing the 10th closest makes it easier to identify the 11. Okay, so today we're going to talk about negative edges. So removing that assumption of positivity, here is a graph that came up a couple of lectures ago, and the question is, what's the length of the minimum walk from S to T? Now, a couple of lectures ago, we realized that this walk had length 0 around the outside. I asked the class if there's any better ones, and it seems like, in fact, there was not. So at the moment, it seems like the best length is 0. Okay. So, okay, good. Now, okay, so negative edges, there is some sort of counterintuitive stuff going on because positive weights is probably how we kind of normally think of geography, and that's more of our natural physical intuition. Negative edges breaks that intuition to some extent, and there's some subtleties that arise. So, for example, take this very simple graph. If I ask Dijkstra's algorithm, in particular the version we discussed, how to get from point A to point D as little as possible, Dijkstra's algorithm in order would decide that A, of course, was at distance 0 from A. Then it would decide that B is at distance 1 from A. And then it would decide that D is at distance 1. Oh, sorry, distance 2. Sorry. Distance 2 from A by going through B. Okay. But then it will continue and say, okay, C is at distance 3. And then only then it realizes, oh, there might be a path of distance 1 from A through D, but by then it's already made up its mind. So this idea that we can, this basic induction argument that I can label distances in order, increasing order from A actually doesn't hold true, because later you might find sort of this very roundabout way to get to D, and that's better. Okay. Another funky thing that comes up with negative edges is negative cycles. So here's a pretty minimal example, and the point is that going around this triangle has a total length of -1. Okay. So consequently, starting from S, we can go here and go around this triangle arbitrarily many times and make the overall walk as negative as we want. So that might have been, I went around, looks like 3 times, plus 2. So this would have been a total length of -1, but of course I could have repeated the triangle and made it arbitrarily negative. Consequently, the distance from S to T is defined as -infinity in this case. So that's another thing that we have to watch out for that did not come up with positive edge weights. Okay, so so negative edge weights kind of prompt some of these weird questions. How are we going to deal with negative cycles? What's also kind of going on with this thing about shortest walks versus shortest paths? At some level, we've all heard these are shortest path problems, but distances are defined in terms of walks, and what happens with negative cycles, and kind of what's kind of going on there. previously was positive weighted graphs because those induction arguments kind of were always naturally increasing. Um, it was always automatically shortest paths, um, uh, even though we're kind of looking for shortest walks. This is made more explicit, even more explicit, when you drop all the edges that don't appear in any shortest walk slash paths, and what's left is a DAG. Okay. And then sort of underlying the whole thing is, in the case of negative edge weights, kind of things aren't so naturally monotonically increasing in distance because you can increase the distance a lot, but then you find a negative edge, you kind of go back, right? You kind of go back in time if we think of edge lengths as time, and okay, that's sort of confusing. So at some level, kind of how do we structure this kind of problem, and figure out how to make things incremental when there's sort of this possibility of kind of going backwards induced by negative edge lengths. Okay. So let me sort of the first thing we're going to do is introduce or discuss a kind of a structural lemma that'll help sort of understand what's going on structurally with negative cycles and this issue of walks versus paths. So here's sort of the lemma. Let's say that I have two vertices S and T, and S can reach T one way or another. Okay, so in particular, the distance is not positive infinity. And the only question is, when is the distance negative infinity and when it is finite? So by definition, if it's finite, then there is a walk attaining the length. Okay. So the claim is that the distance from S to T is finite if and only if that shortest walk attaining the finite distance is attained by the path. Okay. So if there is a shortest if there is a path from S to T that's at least as small in length as any ST walk, then the distance is finite, but actually if and only if. So if is a hard one, but yeah, so the only if is kind of easy. I mean, this is not easy, but the sort of, it's not as large a statement. So suppose there is a path that's at least as small in total length as any walk, then it's a path. So it's a finite number that's being summed. The total length is finite, and that just gives you the distance. So if it is a path, then it has to be finite. That's almost not too interesting. The real question is, the real claim is that if the distance from S to T is finite, then there is a path kind of length equal to L. So let's say that dst is equal to L for some fixed value L. Okay. And now the claim is that there's a path from S to T of total length L. Okay. So in general, just by definition, we know that if the distance is L, then there are walks, possibly more than one walk from S to T with total length L. But the claim is that there is at least one of those walks is a path. Okay. So here's how we're going to kind of set up a proof by contradiction. So one sec, I'm going to give myself a little more space. Okay. So, all right. So let's let W be an ST walk of length L. We know that such a walk exists. But there may be more than one. Okay, so maybe this walk we've drawn is W. But out of all walks of length L, minimizing the number of edges in the walk. Okay, so there may be many shortest walks, but let's take the one that minimizes the number of edges. Okay, and the claim is that W is going to be a path. Okay, so suppose not. Okay, that means W has a cycle. So if I keep working off this picture here, here's maybe a cycle that's in W. Okay, okay. So now we have two possibilities. Let me first set them up, and in each case we'll figure out the contradiction. In one case, the total length of the cycle, if I kind of add up all these, the lengths of all these segments, the length of the cycle is at least 0. And the other case, the other possibility is that the length of the cycle is less than 0. Okay. So here I asked the class kind of in each case how to finish the argument, and the audience did supply the right answer. So first, what is the length? What happens if that cycle is greater than or equal to 0? Then sort of, if I remove the cycle, the total length doesn't go down because I'm removing a non-negative number from the total length, but the number of edges does go down. So if I kind of subtract the cycle, so to speak, it still has length less than or equal to L, so it's still a shortest ST walk, but there's fewer edges. So that contradicts our choice of W, which is supposed to minimize the number of edges. Now, suppose in the remaining case, the length of the cycle is less than 0. And here again, I asked the audience, and a student explained that now if I repeat the cycle, I'll write kind of W plus cycle, so to speak. But let me draw a picture. So kind of starting up here, I go around the cycle. Right now it's just like before, but suppose I go around the cycle again. Suppose I go around the cycle again. Since the length of the cycle is less than 0, if I repeat the cycle, then the total length of that walk with an extra cycle in it is smaller. But it's still an S-T walk, which contradicts L being the minimum. Okay. So what we sort of pointed out is that the minimum length ST walk with the minimum number of edges is always a path, okay, when the distance is finite. Okay, so that's that lemma. But the nice thing is that it characterizes when negative infinity occurs, right? So in part, because negative infinity is sort of a weird thing to think about. So if the distance is finite, then at some level we can focus on paths, and negative cycles, or having any kind of cycle, anything that's a walk but not a path, is completely synonymous with getting a totally negative infinite distance. Okay, so that helps sort out some of these structural aspects, and now we'll focus on algorithmic aspects, which I'm going to frame as sort of how do I kind of figure out the right induction hypothesis to make an algorithm. Okay, how do I because somehow I need to figure out how to structure and organize and make constructive or make sort of incremental uh, my understanding of these as I figure out these shortest paths. But I have to deal with the fact that there could be, negative cycles, and in general, the negative edges sort of push me back in length, decrease the length so far, and stuff like that. So it's not obvious how to produce an induction hypothesis. Here there was many good suggestions from the audience, but it turns out that we have dealt with this before. And we actually have done what we need. So recall that we had looked at this problem of computing the shortest walk from point A to point B with a certain number of edges. And there we did not assume positive edge lengths. But K was arbitrary, the idea, and there we were able to kind of write up this short recursive spec given by matched by an equally simple code, okay. And consequently and if you just kind of save your answers, you apply dynamic programming, you cache your answers, this becomes a very fast algorithm. We sort of have a set of subproblems for every layer I from 1 through k, and for each layer we needed n plus n time because we're kind of working our way through a DAG. Okay, so that was the whole algorithm. Maybe I should have said out loud the recursive spec that works. I actually flipped something from how we did it originally, but the ideas are the same. So we'll define SW, which stands for shortest walk, VI, to be the length of the shortest walk from S to V with at most I edges. And the code is sort of adding one edge at a time to each walk. So if I want to figure out how to get to V using 10 edges, I'll look at all the edges going into V. This is, sorry, there's a typo, or righto, shouldn't say that. Should be the shortest walk to V using 9 edges, or sorry, this is, I'm sorry, let me fix something. Okay, so either I see I had some typos. So okay, it's okay. So if V is not S, we can take the minimum of what we've already had. Say if I'm doing I equal 10, this is using just 9 edges. Or I can try to figure out all the edges coming in to V. Sorry, this should be WV. The length of the shortest walk to W using I minus 1 edges plus the length of that edge from W to V. Okay, so we should have a similar correction down here. There's some typos again. Plus, so I'm looking at all the edges going into V, plus the length from W to V. And then I have one more option, which is, of course, I don't have to use an edge at all. That would be given by SWV I minus 1. Okay, sorry about that. Okay, so much for equally simple recursion. Okay, but hopefully the intuition is clear. I'm trying to figure out the length of the shortest walk from point A to point B using 10 edges, and was, for a particular B was A fixed. I compare it to either how did I get to point B with 9 edges, or I find some other point C, the fastest way to get there 9 edges, and then take one more edge from point C to point B. Okay. So each time I'm just kind of adding another edge. And, okay, and yes, now everything I said about the running time is just fine. We sort of go through the whole DAG once. For each layer, there's k layers, so we need k m plus n time. Okay, so we have this shortest walk algorithm from where I could figure out what's the best way to get from point A to point B using any given number of edges. Again, there is some typos down here. Don't worry too much. At this point, we're going to treat this as a black box. And so suppose we had no negative infinity distance. Suppose there was no negative cycles in particular. The question was sort of how big do I need k to be to figure out all the distances? And I gave this to the audience, and they observed that the class observed that by this lemma from before, if there's no negative infinite distance and I'm only focused on the finite case, then I already know that I only really have to check all the paths from S to T. That means that k equal to n minus 1 gives all the distances. Okay, so if I assume there's no negative cycles, there's no negative infinity, then taking k to be n minus 1 will solve our shortest walk problem, in particular because we recognize that we just need paths. Okay, so the interesting case, or the tough case is when there are some negative infinities, and the question is how best can I sort of identify and keep track and be careful with all of this negative cycle issue. Okay, so let me fix this again. Okay, so there's probably different ways to explain this, but here's the version I put in the notes. Okay, so here's the idea. Each iteration we compute the shortest walks, right? For all these v's. So I'll put like a we figure out the shortest walk to all these different vertices v and I edges, and I use that information to figure out the shortest walk with I plus 1 edges, right? Maybe I can be more precise, which is that when I'm trying to figure out the shortest walk to V using I plus 1 edges, I'm only looking at sort of the shortest walk to various points W maybe W1, W2, using one less edge and seeing if that's useful, where each of these W's have some edge to V. Okay, so, but the point is, the 101st round is based on the 100th, and it's possible that, some vertices, the value does get updated, the value does go down, but for other vertices, it doesn't. There was, using 101 edges instead of 100 edges didn't make a difference. So what I'm doing is I'm introducing a sub k to keep track of the vertices whose distances go down. So these are the vertices that in the kth round, the distance from S to V goes down. So the distance to V using k edges is strictly less than k minus 1. Okay. And I could define bk to be, if I wanted, all of the other vertices. So these are the vertices that do not benefit from the kth edge. Okay. Now, this observation here, right, which is sort of saying that, V's value changes, V's I plus 1 value depends on the W value, means in particular, if none of those W's values changed, then V won't either. Okay, so if I'm just looking at the vertices whose values changed in round 101, it's going to be a subset of sort of the vertices that are one edge away that got updated in the previous round. Okay, so in general, this denotes the out neighborhood of a set of vertices. Say I'll use U since we've already used S. Okay, so these are this kind of the set of vertices V where there's some edge UV where U is in the argument. Okay, so so there's sort of this, the vertices that got updated, they have to be neighbors of vertices that got updated the round before, because this algorithm is sort of adding one edge at a time, so it's sort of information is getting propagated along edges. Okay, so what else does that mean? If I look at the next round, round 102, this is a subset of the vertices that are one step away from the guys who get updated in round 101, and this is a subset of the vertices 2 hops away. Okay. And in general, what you find is that if I'm just looking at round 1000, way in the future, the vertices that are getting updated in round 1000 are a subset of the vertices reachable from A sub k. Okay. So as a picture, in round 100, there's a set of vertices that get updated, and there's some out neighborhood. It could be overlapping, so let me draw it like this. All right, so there could be edges from A sub k to various other vertices. These are the vertices that get updated in round A sub k plus 1. Okay, and in general, whatever is the round in the future, okay, this set everyone needs to be reachable from something that got updated before. Okay, so that's important that this information propagates. Now let's look at in particular A sub n. Okay, so these are the vertices where n edges. So these are the vertices where the nth edge was useful. Somehow the distance went down when you added n edges. Okay. But now remember that if the distance is finite, then the shortest walk is attained by a path. So if there's a vertex in A sub n that somehow is benefiting from n edges, remember a path can have at most n minus 1 edges, then the distance must be infinity. Okay, so that means that for any vertex in this set, A sub n, the distance is negative infinity. Let me give myself a little bit more space. So, okay, so I have all these vertices. Okay. And I have this set A sub n of people being updated. And so what we've shown is that any vertex in this set, there must be some negative cycles. So maybe I should draw something like that, or I guess the negative cycle would have to be inside A sub n. So let me redraw it this way. Or no, it doesn't have to be inside A sub n, but okay. Okay, so there is some kind of negative infinity going on for everyone in A sub n. Now, if I look at any other A sub L bigger, okay, which means that it must be reachable from A sub n, then in particular I can kind of make it arbitrarily negative this way and then go this way. So everyone in A sub L, where L is bigger than n, will also be negative infinity. So anyone who's reachable from A sub n in any single way, since A sub n is negative infinity, will again get negative infinity. Okay. Now anyone who can't be reached, right? So let's say here's A sub n, and everyone that can be reached from A sub n, and then maybe the rest of the graph is not reachable from A sub n. Everything here has some finite distance, which is attained by a path. So it's given by the n minus 1 value, which will necessarily equal the n value. Okay. So in conclusion, what we showed before was that using n minus 1 edges was enough to, in the case where there's no negative cycles and all distances are finite, and we're trying to figure out what to do when there could be negative infinity. And what we've shown is that just by identifying all the vertices that improved on the nth edge, we figured out all of the negative infinities. And in everyone else, their distance after n minus 1 rounds is the right answer. Okay, so all put together, I only have to run it for n rounds, and it's a linear time per round. We now have an mn time algorithm for negative edge lengths. Okay. And this is called sometimes the Bellman-Ford algorithm, although there's other people similar ideas historically, so it's not clear that's the perfect name, but that's the most common name you'll see out there. Okay. All right. So it turns out that this was most of our lecture. I'll mention that one question that came up that I'll leave to the viewer, which is a nice question. So at some level we realized, okay, for finite distances, I should really focus on paths, right? So suggestion was, why are we doing this? Computing the length of the shortest walk. What if we try to compute the length of the shortest path? So the question I pose to you, okay, is let G be directed, okay, with real valued edge weights. Okay. And the goal given two vertices st, is to find the length of the shortest path, okay, from S to T. Okay, so the nice thing about this question is that it's automatically finite. Okay, because there's only a finite number of paths, so you don't have to worry about any negative infinity. And I asked the audience if they thought this problem would be easy or hard, and it was pretty close to 50-50. I think it was like maybe 45% easy, 55% odd. But so it's interesting. Now, so I mentioned that in fact it is hard, and one reduction is from Hamiltonian path. It's easier if you do it from ST Hamiltonian path. So this is really the problem of it's just like Hamiltonian path, but now I give you S and T and ask if there's a Hamiltonian path that starts at S and ends at T. Okay. And so the trick is, I start with a Hamiltonian path problem, even unweighted, right? No edge weights, and I just want to get to S to T, and I want to somehow visit all the edges in the graph, right? So there's some edges, okay? And what we can do is we can add edge length -1 to each one, and then ask for the shortest path from S to T. And if you can find a path with length -n-1, meaning you're using n-1 edges, but it's a path, it's a Hamiltonian path. So if you can find a path of length -n-1, then you get a Hamiltonian path. Okay. But we talked about this at some length, and it was really cool. Okay. And then in the remaining time, I kind of briefly went over this all pair shortest path problem. So instead of just trying to find a distance from S to everyone else, I'm trying to find all ST pairs, and of course you can run single source shortest paths from every choice of S, and the only question is there situations where you can do better in the aggregate? And in this discussion, I'm assuming a negative edge length still, but I'm assuming there's no negative cycles just to make things simple. Okay. Now, so here's sort of there's maybe two different tricks where one can do something a little bit better. So let me explain. Here I've expanded out our recursive specification so that S and T are now both variables, but otherwise it's still the thing we're used to. The length of the shortest walk was at most k edges. Okay. And the idea is to use a doubling trick. So here's something. I'm trying to get from point A to point B using 4 edges, say. And before, I used to try to figure out kind of what I can do in 3 edges and add one more edge. Okay. But here the idea now is that instead I'm going to try to figure out what's the best way to get to any other point C with 2 edges. So I go from A to C with 2 edges, and from C to B with 2 edges, and that gives me at most 4 edges. Okay. But in general, we can do any even power of 2, and that kind of makes it efficient. So if it was paths or walks was at most 8 edges, I could try splitting it in 4 and 4. If it was 16, I could split it 8 and 8. So what you see here is that we're only worried about powers of 2. And if I'm looking at 16 or something, which is 2 to the 4, either I can get from point A to point B using 8 edges, or I can try all the kind of midpoints V, how to get there, how to get to V in 8 edges, and then from V to my destination in 8 edges. And then I'll just return the best one. Okay. So as far as the running time goes, we have n squared choices of s and t, and here's a loop of size n. Okay. So that means it's n cubed times sort of per each power of 2. Okay. But the nice thing is because it's powers of 2, I only need to do log n choices of I before I have 2 to the I is bigger than n, in which case I get all the paths. And remember, there's no negative cycles, so paths are good enough. Okay. So we're left with an n cubed log n running time. All right, so that's the doubling trick. There's a different approach though. That actually departs from some of the stuff we've been doing, and so it's a different induction. It's not an induction on the number of edge lengths. Rather, what we do is we're going to first number the vertices arbitrarily. V1, V2 through V in any particular order is fine. Okay. Now, if I'm going from some point A to some point B, right? There's various intermediate vertices on the way. Okay. You know, various intermediate vertices, VH. And what I'm saying, what we're going to do induction on is saying that all these in-between vertices can only be from V1 through Vk for some various parameter k. So that's what we have here, this recursive spec. I wrote SP for shortest path. SPIJK is the length of the shortest path from Vi to Vj using only V1 through Vk as intermediate vertices. Okay. So, you know, here are some base cases. The interesting thing is here, right? So I'm trying to figure out the shortest way to get from point A to point B using the first 10 vertices. And I have two options. I can either use the first 9 vertices, or if I'm going to use the first 10 vertices, I am going to use that 10th vertex, then I can figure out the best way to get to the 10th vertex using the first 9 vertices, and then the best way to get from that 10th vertex to my destination using the first 9 vertices. I glue it together. As far as running time goes, we have n cubed subproblems. And this only takes constant time now because I'm just trying 2 things for each subproblem. And as a result, you end up with an n cubed running time, which is better than what we just did using the doubling trick. So that is called the Floyd-Warshall algorithm. Again, they are not the only 2 people thinking of similar ideas at the same time. Okay, okay, so much for that. We did not have time to discuss the traveling salesman problem. I'll just mention it now since we're recording. But it's very similar to other stuff we've done. I give you as input a weighted graph. And the goal is to visit all of the vertices in a tour. So a tour has to it's like a walk, starts and ends in the same place, but it visits all of the vertices, starts and ends in the same place. This is actually sometimes called asymmetric TSP or metric TSP out there. There's a couple other definitions you'll find on the internet, but this is the one we're sticking with in the class. If you write asymmetric TSP for directed graphs, there should be 0 ambiguity out there. But that's what we're calling the traveling salesman problem. Just for fun, you know, I was going to note that this is sort of a very famous problem. I'm sure you've heard of it. This is, I guess, some advertisement that Procter & Gamble put out in 1962, asking people to solve a certain traveling salesman problem, trying to figure out the best way to visit all the cities. And okay, fine. But yeah, it's a very important problem. So here's sort of one application, as I understand it, from kind of producing computer chips and chip designs. And the idea is you have like a wafer, right? And uh, you have to you have like a laser that punches holes in like a motherboard or something, some kind of surface, and it has to punch holes in various very specific places to make a chip. And this laser is, very, very refined, and it moves very slowly, and you want to figure out how to get this laser to visit all the places it needs to punch holes in a very specific, in a minimum amount of time, and trying to do this faster um, is a lot, because this is a major bottleneck in producing chips. So uh, okay, so it's a very practical. It's kind of traveling salesman is sort of a very generic and general planning or routing problem where you want to do many things, and you want to do them as fast as possible. Okay, so this problem is hard, and is very similar to the discussion we had on negative links shortest path, but uh, the problem Hamiltonian cycle is hard, as discussed in the lecture notes. There's a reduction from Hamiltonian path to Hamiltonian cycle. Okay. So Hamiltonian cycle is just like Hamiltonian path, except you now start and end at the same place, and otherwise you visit each vertex exactly once. Okay. Now, given a Hamiltonian cycle problem, you could turn into a TSP problem with kind of unweighted edges, and see if there's a way to find a tour with only n total edges, which is the minimum. Okay, and if there is n total edges, then you can solve the Hamiltonian cycle and solve the Hamiltonian path. So that's the basic idea. Okay, so that is it for this lecture. And sorry I forgot to record properly on Tuesday.